So today we have with us Dr. Peter Bijma. After finishing his Master of Science, Dr. Bijma started his PhD at Wageningen University in Research, focusing mainly on predicting the rate of inbreeding in selected populations, together with John Williams of the Rosalind Institute, who became his de facto supervisor. Since his PhD in 2000, Dr. Bijma has been working on several topics, mostly related to quantitative genetic theory, response to selection, and breeding program design. And in 2003, triggered by the work of Bill Muir of Purdue University, he started working on social genetic effects, showing that these effects lead to hidden genetic variation, both in livestock and in natural populations. For this reason, social genetic effects can contribute considerable heritable variation and fundamentally change response to genetic selection, as found for growth rate in pigs and survival in laying hens. Realizing that transmission of infectious disease is a typical case of social interaction, he entered into an inspiring collaboration with Professor Mart de Jong of Wageningen University in Research. Together, they developed a quantitative genetic theory of infectious disease transmission and statistical methods to estimate the genetic effects underlying transmission. The results show that genetic selection against infectious disease is much more promising than currently believed. So thank you for joining us, Dr. Bijma. I'll give the floor over to you.
Thanks a lot, dear audience. So I will tell something about genetics of infectious disease, and particularly how that relates to animal breeding. So here you see my co-workers, Mart de Jong, Professor of Epidemiology, and Dries Hulst, who is a PhD student in our group. So the outline of this talk is that I will first show some theory, focusing mainly on the quantitative genetic theory that links to infectious disease, then a bit briefer on data analysis, on the issue of pathogen coevolution, and finally some ideas on how we could use this in breeding. So starting with part one, the quantitative genetics of the prevalence of infectious diseases. So the trait that I'm focusing on is the prevalence of an endemic infectious disease. If we take an animal breeder's perspective, we typically use binary disease status. So whether individuals are either infected, Y is 0, or either not infected, Y is 0, or they are infected. If we take an epidemiological perspective, epidemiologists more focus on the prevalence, and I will use the symbol P throughout. And the prevalence is essentially the fraction of individuals that is infected at any point in time. But realize, so the prevalence is a fraction, so it's between 0 and 1. So the prevalence actually is just simply the average of the binary disease status that we are used to. So essentially, we are looking at the same trait. Response in binary disease status is the same as response in prevalence. Well, first, a bit of recapping of the classical perspective in animal breeding, which is due to Alan Robertson in a famous paper in 1950. So for binary phenotypes that have an underlying continuous genetic background, we have a so-called threshold model. So on the observed scale, we see the 0-1 trait, but the genetic liability is continuous. And from that model, we can predict that the heritability on the observed scale shows this pattern. So that the heritability is maximum at a prevalence of 1/2, and it goes to 0 if the prevalence comes to 0, and it also goes to 0 if the prevalence would go to 1. Well, if we look at this model, then we see that the heritability disappears. Say this would be an infectious disease. So we select down, we select the prevalence down, and the closer we come to 0, the lower the heritability becomes. So the heritability vanishes if we are almost rid of the disease. So we cannot really get rid of the disease, because if we're close to 0, the heritability is gone. So this is the classical quantitative genetic perspective on binary traits. But in the context of infectious disease, this is not fully correct, because infectious diseases rely on transmission, and transmission is not considered in this model. So this needs an extension. So if we take more an epidemiological perspective, then the prevalence of of an infection, so the fraction of the population that is infected, it's not really a property of a single individual, but it's seen as a property of the population, so a property that is made with all individuals together, a bit like the size of this termite colony. I mean, you can imagine that the size of this colony will depend on the genes of the termites, but you cannot say this is a phenotype of an individual termite. So if we think of the prevalence of an infectious disease, we cannot really use our classical model where the individual phenotype is a combination of genotype and environment, because this phenotype does not belong to a single individual. So if we continue this epidemiological perspective, then it follows from epidemiology that the prevalence depends on what is called R naught. Well, since COVID, we are all familiar with the R value, and R naught is the R value in the beginning of an epidemic when everybody is still susceptible. So R naught is called the basic reproduction number, and it's the average number of individuals that gets infected by one infectious individual if the entire population is not yet infected. And if this value is bigger than 1, then the infection can spread. Well, it follows from basic epidemiological theory that the prevalence of an endemic infection, so the fraction of individuals that is on average infected, is given by this equation. So it's fully determined by R naught. And this equation is plotted here. So if R naught is below 1, the disease cannot spread, it dies out. And if R naught is higher, we see an increasing equilibrium prevalence. The increase is steep in the beginning and it flattens off later on, and it asymptotes to 100%. So because epidemiology tells us that prevalence depends on R naught, this means that if we want to understand the genetics of prevalence, we must understand the quantitative genetics of R naught. So that is what we set out to do. So then we have to think about what are the genetic factors that determine R naught. Well, so R naught is remember, R naught is the number of individuals that get infected by a single infected individual, if everybody is not yet infected. Well, that will depend on the contact rate. I mean, if animals have more contact, there's more transmission. It will also depend on the susceptibility of individuals. I mean, if they are easily infected, if there's little resistance, more individuals will become infected. It will depend on the infectivity, so say the amount of pathogens that individuals spread. And it will depend on the duration of the infectious period. If individuals are infectious for a very long time, they will on average infect more other individuals. Well, then basic epidemiological theory shows that R naught is the product of the contact rate, the mean susceptibility, mean infectivity, and the mean duration of the infectious period. Well, this is a multiplicative model, and that's not very convenient for breeding and quantitative genetics, because we like to work with additive models. But if we look at a logarithmic scale, then this leads to an additive model for the logarithm of R naught. So with a bit of mathematics, we can show that the breeding value for the logarithm of R naught is the breeding value for susceptibility plus the breeding value of infectivity plus the breeding value for the duration of the infectious period. So this breeding value for R naught plays a very central role in the quantitative genetics of infectious disease. So from the breeding value for the logarithm of R naught, we started to derive breeding values for individual phenotype and breeding values for response to selection. And in the example that I will show here, we assume for simplicity of the presentation here that there is no genetic variation in infectivity, because then the result is a bit more complex. So let's first look at the usual breeding value for individual disease status. So for own phenotype, the 0-1 binary disease status. With a bit of mathematics, we can show that the breeding value for the disease status of an individual depends on the breeding value for the logarithm of R naught of that individual multiplied by some factor that depends on the prevalence. So to illustrate what this means, this is just an ordinary breeding value that predicts the phenotype of an individual. So suppose we have a population with a prevalence of 20%. So on average, 20% of individuals are infected and 80% are not infected. And in this population, we have an individual with a breeding value of -2%. Then we expect that this individual has an average phenotype of 0.18, meaning that is 18% of the time it will be infected. So this is just an ordinary breeding value where the expected value of the phenotype is simply the average plus the breeding value. What we also did, we looked at response to selection, and it appears with a bit of mathematics that you can also show that this breeding value for the logarithm of R0 allows you to derive a breeding value for prevalence, so for response to selection. So importantly, the breeding value for own phenotype predicts what this individual phenotype does, but the breeding value for prevalence refers to the average of the population. Well, that breeding value is shown here. And also the breeding value for prevalence is a simple function of the breeding value for the logarithm of R0. So, but the interpretation is a bit different because this breeding value is predictive of response to selection. So as usual, response to selection is the change in the average breeding value for prevalence. So as an example, suppose again we have this population with a prevalence of 20%. We have a group of parents that we select, and on average they have a breeding value of -2%. Then in the offspring generation, the prevalence will have gone down to 18%. So this is all sort of as usual, but if you now look at those two equations, you will see that they are different. We have a factor P here, which is not present here. So these two breeding values, the breeding value for own phenotype and the breeding value that predicts response to selection, they differ by a factor equal to the prevalence. So the breeding value that predicts individual phenotype and the breeding value that predicts response to selection are no longer the same. And that's very unusual compared to our classical theory. So an important message is that the usual breeding value that determines individual phenotype and the breeding value that determines response to selection, they differ by a factor equal to the prevalence of the infection in the population. And the reason that this happens is because the ordinary breeding value does not include the effects of transmission of the infection, whereas this does matter for response to selection. So let's look at an example. Suppose again we have this population where on average 20% of individuals is infected. And then we have an individual with a breeding value of -2%. Well, as I showed in a previous slide, we expect that this individual is infected 18% of the time because its expected phenotype is 0.18. However, now suppose we would select a group of individuals that has an average breeding value for individual phenotype of -2%. So we select a group of parents for the next generation. Their average breeding value for individual phenotype is -2%. And we are interested in response to selection. Well, for response to selection, we should not look at the breeding value for individual phenotype, but we should look at the breeding value for prevalence. Well, and I mentioned that they differ by a factor equal to the prevalence. So we have to get response to selection. We have to divide this breeding value for individual phenotype by the prevalence of the infection. And then the breeding value for prevalence is -10%. So this means that if we select this group of parents, the prevalence goes down from 20 to 10%, not to 18, but it goes down to 5-fold. And this 5-fold is not a coincidence because the prevalence was initially 1 in 5. So we get 5 times more response than we expect from classical theory. So in contrast to the usual case, we have distinct breeding values for individual phenotype and for response to selection. And they differ by a factor equal to the prevalence. So for a single individual, I have plotted the two breeding values here. So this is the breeding value for individual phenotype. And this is the breeding value for response to selection, for prevalence. And on the x-axis, you see the prevalence. So the breeding value depends on the prevalence of the infection in the population. And the one for individual phenotype is a bit like the classical 0-1 trait. It goes to 0 if prevalence goes down. But the breeding value for response to selection becomes larger and larger the more rare the infection is. Well, if the breeding values differ, it also means that additive genetic variance must differ, because the additive genetic variance is just the variance of the breeding values. So on the next slide, I show heritability, so additive genetic variance relative to phenotypic variance. Here you see the usual heritability for individual phenotype. And the pattern here is very similar to the what I showed in the beginning, the result of Robertson, that heritability has a maximum at the population average prevalence of 1/2, and it goes down if prevalence goes to 0. So the genetic component of individual phenotype becomes smaller and smaller if the disease becomes rare. But for response to selection, this is totally different. So we can also define a heritability that represents potential response to selection, and the symbol for that is T squared. And well, I developed this in the context of social interactions, and if you want to read about this, then most of that work is in this paper. But what you see here is that if the disease becomes more rare, so if the prevalence of the disease goes down, the heritability increases. Which also means that if we select for a lower prevalence of the disease, the heritability goes up instead of down. And that suggests that actually it becomes easier to further decrease the prevalence of the disease instead of more difficult. Well, so what we see here is that most of the genetic variance is hidden, in the sense that we see only a fraction. If I go back to the previous slide, I mean, this traditional heritability is what we see in the individual phenotype. But there's much more heritability that we don't see, that we can use for response to selection, but we don't see it in the individual phenotype. So we talk about dark genes. Oh, sorry. As an analogy of dark matter, I mean, you will probably know that most of the matter in the universe is hidden, so we cannot see it. And as an analogy with infectious disease, most of the genetic variation we cannot see. It's hidden in the transmission process. And that is illustrated by this figure. This is a little bit of a complex figure, but so on the x-axis, you see the prevalence of the infection. So here the infection is very common, nearly everybody is infected, and here it's very rare. And this dark solid line shows the total genetic variation for constant genetic parameters on the underlying scale. So we see that the total genetic variation increases. Well, and we also I have also plotted the components due to the usual breeding value of individual phenotype, the direct effect, and that is this blue line. And that almost completely disappears if the disease becomes more rare. So particularly if the disease becomes rare, most of the genetic variance that we see is hidden. It's hidden in the indirect genetic effect, so the effect of transmission, and in the covariance between direct and indirect effect. Well, the main message here is that most of the genetic variation that we can use as breeders to generate response to selection, most of that genetic variation is hidden in the transmission process. Well, let's look at what this means for response to selection in the prevalence of an infection. If you think of classical animal breeding theory, then we have the breeder's equation, and the breeder's equation says that response to selection is intensity of selection times the accuracy of selection times the additive genetic standard deviation. So this is our classical, these dark symbols, black symbols are the classical breeder's equation. And I mentioned that the breeding values differ by a factor equal to 1 divided by the prevalence. So that suggests we should simply be able to upscale our classical prediction of response by a factor 1 over prevalence. So if the prevalence is 20%, theory predicts that we should get 5 times more response. Well, we tested that with a simulation. So we did a very standard stochastic simulation of endemics. We don't use any of the theory that has been presented here, and very simple mass selection. So in this figure, you see response to selection. On the x-axis is the time, so these are generations. And on the y-axis is the prevalence. And I have 2 cases. One where the population starts at a prevalence of 50%. So initially 50% of the population is infected. And another one where the population starts at a very high prevalence of 95%. Well, then you see the small open circles. The small open circles are the results from the simulation. So simulation shows that initially, if we start at a high prevalence, initially very little happens, and then response goes faster and faster and faster, and here we get eradication. And if we start off with a prevalence of 50%, essentially we see this part, which is essentially the same as the end part here. I have also plotted 2 predictions in this figure. The red dashed line is the classical breeding value, so the breeding value of our own phenotype. We see it here and here, and it's way off of the results of simulation. I mean, it predicts way less response to selection. And the blue line is the prediction that I show here on the other side, where we have upscaled response by a factor 1 over prevalence, and that very nicely matches the theoretical prediction very nicely matches the result from standard simulation of endemics. So our theory agrees with classical epidemiological methods. So why does this happen? Because this is very different from ordinary results in animal breeding. Well, the reason that this happens has to do with feedback. Suppose we have 2 categories of individuals. We have individuals that are not infected and they can become infected, so we call them susceptible. So susceptible individuals can become infected and then they can recover and become susceptible again. The rate at which susceptible individuals become infected depends on the number of infected individuals. I mean, you can imagine if there are many infected individuals that are spreading pathogens, then more new individuals will become infected. So if we do a little bit of breeding to reduce this transmission, then the number of infectious individuals will go down. That will reduce this rate at which the infection happens. So we have a positive feedback loop here. In other words, suppose we have an individual that is less susceptible to become infected, for example, due to breeding. Well, then it's not only that this individual will be less often infected itself, but it will also infect fewer others, simply because it's not so often infected. So it's the feedback loop and the transmission that generates this result. And we also see that if we simulate transmission of an infectious disease. So here we see the population starting at an initial prevalence of 25%. And then on the x-axis, you see cycles of the transmission loop. So these are not generations of selection, but this is the transmission finding its new equilibrium in the population. So then suppose we select a bunch of parents that have an average breeding value of -1%. Then initially we see a drop from 25 to 24. But then because the number of infectious individuals has dropped to 24%, we get less transmission, and so we see that effect continuing. And we in total for this situation, we get a response to selection of 4% instead of 1%. And this 4% is not a coincidence. I mean, this is 4 times 1%, and this factor 4 is 1 divided by 0.25. So if we do the same, and we start off with a prevalence of 12.5%, which is 1 in 8, then initially response is 1%, but then it asymptotes to the 8-fold. So this bigger response to selection is due to positive feedback in the transmission. Well, we made a number of assumptions in this model, and the key assumption is that the pathogen replicates only in the host individual, so only in the livestock. So there is not a secondary host, which means that if we have individuals that are more resistant to infection, we get fewer infected individuals, and therefore we get reduced exposure. Importantly, this is about replication of the pathogen. It's not about survival of the pathogen. I mean, very often pathogens survive in the environment for some time, and that doesn't matter. Another thing is that we have not looked into the co-evolution of the pathogen. I mean, typically if you select livestock, then the pathogens also shows an evolutionary response. But I will talk about that in a few slides below. So this is the final slide of the theoretical part. So we have developed an integrated theory of epidemiology and quantitative genetics. And central to this theory is the breeding value for the logarithm of R0. And the results show that response to selection is a factor 1 divided by prevalence greater than we would expect. And this also means that response to selection goes faster the more rare the disease becomes. And so the more rare a disease becomes, we increasingly see that hidden genetic variation, so dark genes, dominate response to selection and genetic variation. So we get more response than we think based on classical quantitative additive genetic variants. So that was the end of the theoretical part. We are more recently we started working on data analysis, so estimation of these genetic variances and breeding values, and we did this together with Andrea Wilson and Ricardo Pong Wong of the Roslin Institute. So if we think a bit about what is it that we want to estimate ideally? Well, if we are working in genetic improvement of livestock or plants, and the ultimate objective is response to selection. So we want to estimate the genetic parameters and the breeding values that determine response to selection in the prevalence of the infection. Well, we know that prevalence depends on R0, and the breeding value for the logarithm of R0 is the sum of the breeding values for susceptibility, infectivity, and the recovery rate. So these are the genetic parameters and breeding values that we want to estimate. So if you think a bit about that, if you think about susceptibility, infectivity, recovery, what we need to observe is transmission and recovery events. Not so much the individual disease status, but we ideally want to observe that individuals become infected. So we see transmission and then they recover. So to do that, the data that we need, and I see there's a typo here. This is supposed to be longitudinal. The ideal data that we would like are longitudinal data on individual disease status, so that we see when an individual becomes infected and how long it takes that it recovers. And the time interval is crucial, as we will see in the results. What we also need to know is the exposure. So we need to know the group of individuals that could infect each other. So, for example, pigs in pens or herds in dairy cattle, for example. So we need the contact structure or the group structure. So we did simulation and subsequent analysis of the data with the objective to estimate genetic parameters and breeding values for susceptibility. So I only talk about susceptibility here. We have not yet looked into infectivity and recovery. So we simulated epidemics in a population that consisted of groups, and the transmission is within the group. So we have a population consisting of many groups, and the transmission of the infection takes place within the group. And we simulated transmission and recovery. So in principle, in the simulation, we know the disease status for each individual at any time. We know whether they are susceptible, infected, or recovered. Well, and we did this for a range of genetic parameters, but the maximum observed scale heritability that we had is 12.5%. Well, that's already fairly high, but most results I will show have a much lower heritability. Well, then from the simulation, we generated data sets. And what we want to observe in this data are infection events, because we look at susceptibility, so I'm not interested in recovery here. So we transformed the data in the format that you see here. So for each individual, if we see a 0, it means it did not become infected in that time period. So we have longitudinal data, so we look at time periods. So the individual that we see here, in the first 4 time periods, it did not get infected. Then in the 5th time period, it got infected. And then afterwards, we have no data on this individual anymore because it is already infected. So we cannot observe its susceptibility anymore. So, and we collected these data from the simulation with different time intervals. And then we fitted a generalized linear mixed model. And that generalized linear mixed model is not founded on statistical considerations, but it is really derived from the transmission process. From the epidemiological theory, we know how the transmission works. And from that, we can derive what sort of a generalized linear mixed model we need. So the model is shown here. So we have a link function, and we can show that we need a so-called complementary log-log link function. So not a logit or a probit, but a different one. Then we have an intercept, a group effect, a time effect. These are fixed effects. We have a random interaction between group and time. We have an additive animal genetic effect. Well, we have repeated observations, as you can see here. So we have a permanent environmental effect. And here we have something that is fairly common in generalized linear models, which is an offset. And this offset accounts for the exposure, so for the fraction of infected individuals in the group, and also for the duration of the time interval. So we tested the performance of this model. And then it appeared that we should remove the fixed effects for group and time, because they absorb too much exposure. And as a consequence, the estimates go completely off. So we dropped the group and time fixed effects. We also discovered that we need to keep the group time random interaction to avoid overestimation. And you can see it on these results. So on the x-axis here is the sampling interval in both figures. And in the figure B, we see the estimated genetic variance in susceptibility. And the horizontal line here is a true value. And then we have 2 models. And the model 4, which is shown in the triangles, model 4 does not contain this random interaction. And then we see that particularly for somewhat larger sampling intervals, if we don't fit this random interaction, then we get quite a bit of overestimation, that the estimated genetic variance is quite a bit higher than the true value. Whereas if we fit the model that does have this interaction, we see that the interaction absorbs more and more variance if the sampling interval between records is larger. So a group time interaction is important. So based on these considerations, we chose for a reduced model where we dropped the group and time effect. So the resulting model is shown here. So the fixed effects are gone, but the random interaction is still present. And then we looked at what had an impact on the quality of the genetic estimates. And the key factor is the observation interval. So the closer our observations are together, the better the estimate is. So in figure A, you see the bias. for 3 levels of heritability. Here the heritability is 0. And the estimates are not exactly 0 because, I mean, variance estimates cannot be negative, so we get a little bit of positive bias as usual. Here we see an intermediate heritability, and here we see a higher heritability. And we see that if the sampling interval is 1 day, then our estimates are spot on the true value. If the sampling interval becomes larger, we go to the right, then we get a bit of overestimation here and here a bit less. So there's clearly bias if we sample with a somewhat larger time interval. Well, in figure B, you see the precision in a sense that you see the standard deviation of individual estimates. And the nice thing to see is there that for the estimates where the true value is 0, the estimates are also not significantly different from 0. So we need short time intervals to accurately estimate breeding values for susceptibility. So the conclusions on the second part on data analysis is that we can estimate genetic parameters for susceptibility. We need longitudinal data on individual disease states, so we need time series data of individual disease status. Ideally, we have short observation intervals, and we need a generalized linear mixed model that is founded in the transmission dynamics. So not just a logit or a probit generalized linear mixed model. Well, this is for susceptibility. The next step that we will work on is infectivity, which is difficult. Well, it's not difficult in a sense of modeling, but infectivity is more difficult to estimate because it is easily confounded with group effects and things like that. And a further thing we also want to do is to estimate recovery. Well, that finishes the second part. So now I will go to the third part, which is co-evolution of the pathogen. So Dries Hulst, the PhD student who was on the first page, has done some modeling of pathogen co-evolution. I mean, the typical problem is if you generate or introduce disease resistance, you will see that the pathogen adapts and the pathogen may escape the resistance of the host. So if we breed for disease resistance, the pathogen may actually adapt and be still present. Well, when we did some modeling, well, we took the assumption that escape mutants, they may just arise. They may arise at any time because we cannot contribute mutation. We cannot control mutation. So we have to control that the mutation spreads in the population. And the problem is that, as we found from the modeling, is that if you select for disease resistance, there will typically be a time window where new mutants can invade the livestock population. So mutants that confer resistance to the pathogen, that they can invade the host population. Well, this can happen if we get a mutant that can escape the resistance. So of course we need a mutant that is not to which our livestock are no longer susceptible, no longer resistant. The mutant must be better than the wild type. So this invasion window starts when the mutant spreads better than the wild type pathogen. And importantly, the invasion window ends when the pathogen is locally eradicated. I mean, we cannot get new mutations if the pathogen is no longer present. So, well, here this is a bit a complex figure, but don't worry about the detail. Just focus on the message. So on the x-axis, you see the frequency of a resistance gene. Suppose we have a resistance gene that we want to introduce in a cattle or a pig population. If we introduce that gene, initially the mutant bacteria or mutant viruses cannot invade because the wild type is better. Then at some stage the mutant becomes better than the wild type, and we get a window where the mutant can invade. And then if the host resistant gene is at a higher frequency, we see that the wild type has been eradicated, so the disease is no longer, or the infection is no longer present, the pathogen is no longer present, so the mutant cannot arise. So if we want to avoid pathogen co-adaptation, we have to move through this window as quickly as possible, and we have to make the window as small as possible. So thinking about this, if we want to avoid pathogen co-evolution, well, there is an analogy with other well-known cases of, say, pathogen evolution. First, if you think of HIV medication, and as far as you're familiar with that, HIV medication has only become successful when multiple medicines are combined together, because then it's unlikely that there's a mutant that escapes all of them. So the analogy with genetics is that polygenic resistance is more sustainable than single gene resistance, because it takes longer time before a mutant will happen that can escape all resistance mechanisms. Well, there's a second analogy with antibiotic resistance. I mean, there's a considerable problem of resistance of bacteria to antibiotics. And to prevent bacteria becoming resistant to antibiotics, the key thing is that a sufficient dose is needed, that the bacteria are killed quickly. So the analogy for breeding is that we should move the population through this invasion window as quickly as possible, which has two components: a high response to selection and a small window. Well, this is typically not possible on the population level, because in breeding we typically select for a multi-trait breeding goal where we make small steps of improvement in each of the traits. So on the population level, this is actually quite hard. So this suggests that we would have to take a more, say, herd focus, where, for example, by starting on breeding values for resistance, that we make a group of for example, a group of bulls or a group of animals that we move into a herd that have an extremely high breeding value for resistance. And combining that with hygiene measures, we could potentially get herd-wise eradication, so that the window in which mutations could happen that escape the resistance is very small. Well, if you think of current animal breeding, we are kind of doing the opposite. I mean, we are doing gradual multi-trait selection. So we're making small steps in all traits, including disease resistance. And that is very similar to using low doses of antibiotics for a long time. So it is actually quite likely that our current multi-trait selection, that we are breeding resistant pathogens. So, well, I think we would need a proof of principle and see whether this could really work. Well, this finishes the third part. So I now have a few ideas on how this could be used, and these ideas could be used in breeding. So what should we do based on these findings that I showed? One thing that we have observed is that response to selection is the largest at low prevalence. And this suggests that we should combine genetic selection with other measures. So instead of thinking if, for example, if we take hygienic measures, then genetic selection is not so important anymore. It's not like that. If we take other measures such as hygiene, isolation, vaccination, etc., then actually genetic selection becomes more important. And I illustrate that here in the simulation. So on the x-axis is time, and on the y-axis is the prevalence. And we start off at a population where 25% of the individuals is on average infected. And suppose we're looking at a selection strategy where, in principle, we could reduce the prevalence by 4%. Now suppose we take some hygienic measures before we start selecting, and that already reduces prevalence to here 16%. And then we apply the same selection as I shown here with this 4%. So that selection starts here. Then what we see is that prevalence doesn't drop by an additional 4%, but it drops by 7%. And this is because response to selection is higher. If we make the same genetic change, response to selection prevalence is higher at lower prevalence. So we get an extra benefit if we combine breeding with other measures that reduce the prevalence of an infection. Well, another thing that we have seen is that longitudinal data on disease status are ideal. And this, I think, means that we have to invest in sensors, computer vision, and AI systems to get much better data on individual disease status. I mean, these things are all under development, but these developments are actually going quite fast. So maybe in 10 years' time or so, we have much better data on individual disease status. Well, if you think of pathogen, preventing co-evolution of the pathogen, well, just like antibiotic resistance, where we need a high dose of antibiotics, to prevent co-evolution, we need strong selection. So that suggests we maybe have to do this herd-wise, and we have to combine selection with management interventions because the response to selection is larger if we already have a low prevalence. Well, what should we not do based on theoretical considerations? Well, actually, we should not do what we are currently doing, which is gradual selection for a multi-trait breeding goal, because we are not only making the livestock better, but also the pathogen. Well, maybe this is still quite a bit better than doing nothing, but certainly there are questions on impacts on pathogen coevolution due to the current breeding strategies. Well, I planned for 45 minutes. I'm 2 minutes late, so that's not too bad. So this was my final slide. So I think we can now have. There's time for some questions if you have.
Thank you, Dr. Bijma. If anyone has any questions, feel free to raise your hands. You can turn on your microphones and cameras. Or if you want, you can enter any questions into the chat. Colin, go ahead.
Hey, Peter, how are you doing?
Hey, Colin, good to see you. I'm doing fine, thanks.
Good. I think it's probably, I should be the one to ask you the first question, considering I should have more knowledge than the basic consumer on this topic. But so one of your main concerns with kind of going towards susceptibility as itself, as you mentioned, was with respect to creating those kind of mutant pathogens, essentially, and then you're kind of restarting your process again in terms of then putting selection to reduce those mutant bugs that you're creating. So what is your opinions around the resiliency, going towards resiliency, so that you're still keeping the same bugs in the population and you avoid that kind of mutant pathogen developing?
So if I understand correctly, you're asking about resilience rather than, say, resistance?
Yes.
Yeah. Well, I have to rely on what I heard from Mark de Jong in this context. So selection for resilience, it can work, but there is also a risk that you get actually that it introduces selection for spreading. But it depends on the specific case. So I cannot properly answer that. I think what I have not. I mean, my background is animal breeding and not in the epidemiology, so I'm sort of only recently in epidemiology. So, but there is a risk if you select for resilience that you get more spreading, because the animals that spread more, or say the pathogen that spread more, has a selective advantage. so that you get more spreading of the infection. And it, of course, it also really depends on the infection that you're talking about. I mean, if you have an infection that is not only harmful to animals, but potentially also to humans, so if you have a zoonosis, that's of course then not something you would want to do.
Perfect, thank you.
Any other questions? I was sort of wondering when you were talking about R naught,
Yes.
there's a few, I guess, determinants of that, and then you said kind of contact between individuals and stuff like that. So how would you determine that in your animals? How would you kind of determine?
Yeah, well,
like
you can
what
actually,
data would you need to collect?
Yeah, so if you have these longitudinal data that I showed, that I discussed, I'll go a few slides. Can you actually still see my slides or not?
Yes.
Yeah, okay, yeah. So in this linear model, and you could drop the random effects, etc. But if you fit this generalized linear model to longitudinal disease data, this intercept gives you an estimate of the effective contact rate.
Okay.
So you don't need to observe contacts, or so you can estimate it from the spreading of the infection.
Okay.
And you don't need large data sets. I mean, for the estimation of genetic parameters, you need way more data, but for the basic transmission, you don't need these amounts of data. So that can reasonably well be done, yeah.
Okay.
And people in epidemiology have quite a bit of experience with that. Yeah.
And I guess, yeah. Oh, Flavio, go ahead.
Hi, Peter.
Hi.
Can you hear me?
Almost.
Almost. Okay, now
it's
better
fine.
now?
Yeah, now it's
Okay.
clear. Yeah.
Okay, yeah. Great presentation. Thank you for doing this. I have a question. It's more a curiosity, because all the theory that you present is based on the fact that these diseases are polygenic in nature, right? And in your simulation, probably you simulated a polygenic trait.
Yeah, we simulate polygenic trait. Yeah. I mean, it's
my question
the basic
is,
principles are not the basic principles are not different, but I mean the fit is not as good, I think. But the basic principles, I think, are largely the same also for single genes.
yeah, but have you tried to simulate oligogenes? I'm not saying just one gene, but a few genes to see the impact on the. Because you had the simulated data instead of
we have just simulated a full polygenic trait. So essentially, we just simulated normally distributed breeding values on the underlying scale.
Yeah. Are you planning to do that?
Not really, because I'm not so convinced it will be so much different. So I'm not. I'm not.
Yeah. Because if you have a really major genes affect the trait, then let's say that the animals really that get sick, they are homozygous for right for that, and then you are going to have always the heterozygous there. That is very difficult to eliminate from the population, right? So you are going to have those carriers that are really hard to eliminate them. I don't know. I know it might be
So
a little bit different.
If you have a fully recessive major gene,
exactly.
Then I mean, if I would do this, I would definitely do this with molecular data. So I mean, for polygenic cases with genomic prediction, that's where I think the power really comes in if you combine good phenotypic data on disease status with genomic prediction. I would not go for this without genomics.
No. Yeah, you could, but I just wonder if the response will be exactly the same as you predict when you have a fewer genes. and the genes would, well, then you have to decide if they are going to work with just additive or genes that no are recessive. But anyway, it was just
Yeah,
was
okay.
curious.
Yeah, I mean, you of course, if you have a single gene that is it is recessive, you will see that genetic variance changes quite a bit over the trajectory of the allele frequency. So
Yes.
yeah, so things will start to change. But I think the phenomena that are due to the transmission, so the extra genetic variation due to the transmission, I don't think that fundamentally changes.
Yeah. Okay. Thanks again.
You're welcome.
Okay. Do we have any more questions?
Maybe I scared you off a bit with a lot of theory. It's anyway, it's recorded. So
yeah. What about herd immunity? Does it kind of affect anything?
well, this is, I mean, this herd immunity is I mean, let me go up a few slides. So here where we put epidemic simulation next to the theory, at the bottom, I saw here you see eradication, and here as well. And actually, this is the point where we reach herd immunity.
Okay.
So so the main new insight, I think, is that we can, with genetics, we can in principle reach herd immunity. I mean, from the classical theory, if we again go up a few slides, I mean, classical theory, heritability behaves like this, and so it goes to zero if we get close to herd immunity. But due to transmission, that doesn't happen. Actually, the heritability goes up, and we see that if we look at this figure. I mean, if we get to lower values on the y-axis, the response to selection goes faster and faster and faster, and here we reach herd immunity. So one of the messages is that we can reach, at least in theory, in contrast to classical theory, we can reach herd immunity with genetic selection.
Okay. Interesting. Okay. If nobody else has any questions, I don't think, is anything in the chat? Look like it. Okay, well, thank you for everyone that joined us today, and thank you, Dr. Bijma, for the great presentation. Yeah, see everyone next week. Have a nice weekend, and
okay.
Thank you.
Thank you. Bye-bye.
Bye.